I'm really excited to be here. As Jordan mentioned, I'm Matt Austin, postdoc through the Living Earth Collaborative with WashU, where I've been working in close collaboration with the Surrey Botanical Garden. Before I begin, I'd like to take a moment to thank the many people who have worked with me on the research that I'll be talking about today. I wish I had sufficient time to thank everybody who's contributed to this work, but I'd like to give a special thanks to my three advisors, Adam Smith, Ken Olson, and my PhD advisor, Amy Dunlap. The focus of my talk will be on how herbaria can be used in novel ways to support botanical research and conservation. And I'll be subdividing my talk into two components. In the first part of my talk, I'll chat about some of my prior research using herbaria as sources of long-term data to test how climate change has affected plant reproduction. And then in the second part of my talk, I'll chat about some of my future directions for utilizing herbarium data, and in particular, digitized herbarium data for supporting botanical research and conservation. But before moving into either of these, I'd like to give you all the backstory of how I was led to the herbarium. So my trajectory to herbarium research begins from gaining an early interest in the utility of biological collections for supporting conservation at the very onset of my PhD. For example, the first chapter of my PhD used specimen data of bumblebees from various natural history collections, where I was interested in whether trait data from entomological collections could be used to test the hypothesis that interspecific trait variation is positively associated with changes in relative abundance across the past century. So I performed a study taking trait data on bumblebees from the Smithsonian, Field Museum, American Museum of Natural History, and the Illinois Natural History Survey to test whether measures of interspecific trait variation are associated with change in relative abundance as calculated via IUCN assessments. And I found support for that hypothesis with a positive correlation between change in relative abundance and interspecific variation, where species with greater variation are more likely to have increased in relative abundance across the past century, and species with lower variation are more likely to have declined. So I took an early interest in the utility of biological collections. However, one study from my PhD in particular led me to the questions that I've been using herbaria to answer in my postdoc today. And this is a study looking at the effect of co-flowering richness on patterns of pollinator movement between flowers. Pollinator movement can broadly be subdivided into either floral constancy, where a pollinator makes repeated consecutive visits to flowers of the same species, and thus is likely to transfer pollen intraspecifically. And floral constancy contrasts with floral inconstancy, where a pollinator makes repeated consecutive visits to flowers of different species, thus risking heterospecific pollen transfer. I performed a behavioral experiment where I tested the effect of co-flowering richness, so either fewer species flowering at the same time in an environment versus an environment with a higher number of species flowering at the same time, and looked at the effect of co-flowering richness on floral constancy, and found that environments with a higher number of co-flowering species are likely to induce the random movement of pollinators between flowers, and thus co-flowering richness should promote heterospecific pollen transfer. So this study led me to become interested in how herbaria could be used to test what environmental aspects affect co-flowering richness, and also how does the environment affect outcrossing rates of flowering plants. And since becoming involved in herbarium research to answer these questions, I've been involved in a variety of herbarium-based research projects. I wish I had time to chat about all of these today, but for time, in the first half of my talk, I'll be chatting about just two of these projects. However, I'd be happy to talk in more depth with any of you about any or all of the herbarium-based research that I've been involved in throughout my career. So these two projects that I'd like to chat about in the first half of my talk are both related to answering two different questions. The first being, how do changes to flowering time affect co-flowering richness at the community level? And the second being, how does climate change affect outcrossing rates of flowering plants? So let's begin with the first of these two questions. When I became interested in exploring the effects of the environment on co-flowering richness, I became interested in whether changes to flowering time that are being induced across taxa by climate change might affect levels of co-flowering. In other words, we know that one of the most ubiquitous ecological effects of a changing climate are changes to flowering time. However, not all species are changing their phenology in the same way. There's a high degree of interspecific variation in both the direction and magnitude of flowering phenology changes. And thus, I became interested in whether the high degree of interspecific variation in changes to flowering time might affect co-flowering richness, whereby as species change their flowering time at different rates between species, might species that used to have flowered at different times of the year now be overlapping, or vice versa? Species that used to overlap, might they now have partitioned flowering time? So to answer this question, I began collaborating with a group based out of the Missouri Botanical Garden, who holds a long-term data set of field collected flowering data from Shaw Nature Reserve. And this group was led by Peter Hoke, Nicole Miller-Strutman, and Kira Krakos, who around a decade and a half ago, when Nicole and Kira were students of Peter, they found in the Missouri Botanical Gardens archives records collected by Edgar Anderson, the former director of the Missouri Botanical Garden, where these records had documented flowering times at the community level from Shaw Nature Reserve from 1938 through 1941. And as Peter, Nicole, and Kira parsed through Anderson's records, they realized that Anderson had gone on weekly nature walks at Shaw, and every week he recorded every species of plant that he saw in flower that week. And by doing this, every week from 1938 through 1941, they realized that this was a valuable historic data set to which contemporary flowering records could be compared. And thus, from 2009 to 2012, Peter, Nicole, and Kira repeated Anderson's flowering observations, where they ascertained from Anderson's notes that the rough area of the reserve that he was sampling is, for those of you familiar with the reserve, the Goddard River Trail and the Wildflower Loop. And Peter, Nicole, and Kira walked those loops every week from 2009 to 2012, and just like Anderson, recorded every species in flower every week. After collecting their data, they also realized that James Traeger had collected opportunistic flowering records from throughout the reserve from the 1970s through the 1990s, which they added to their data set. So when I began collaborating with this group, I added for every species in the data set herbarium records that span from 1850 to 2017 from the counties immediately surrounding Shaw. And those counties are shown highlighted in blue here, with the midpoint of Shaw being indicated by the red dot. And I'll circle back to the utility of these herbarium records later in the talk. So how did I use these data to test whether changes to flowering time have affected co-flowering richness? To look at how I went about answering this question, I think it's helpful to zoom in on just one species in this data set to see what the data look like. So here we see data for Conoclinium celestinum, the blue mist flower, where we have day of year on the Y plotted against year on the X. Every point is a flowering record. And on the left here, we see Anderson's observations. On the right, the observations from Peter, Nicole, and Kira. And in the middle, the opportunistic records collected by James Prager. Here are the herbarium records that I added for the species spanning the late 1800s through the early 2000s. And now, to test how changes to flowering time have affected co-flowering richness, what we need to do is test how the duration of each species flowering season has changed across time, and then we can use changes to duration to look at changes to the overlap of different species flowering seasons. So I went about this by performing, for every species in the data set, a 10th quantile and a 90th quantile Bayesian regression, where the slope of the 10th quantile line gives an estimate for how the beginning of the species flowering season has changed across the past century. And the slope of the 90th quantile line gives an estimate of how the ending of a species flowering season has changed across that time. By taking the 10th to 90th interquantile range, we derive an estimate of how the duration of that species flowering season has changed across years. So I did these analyses for every species in this data set. There are 68 species total, with data spanning more than 160 years and over 6,000 flowering records. Around 4,000 of those are derived from the field and just under 2,000 from the herbarium. For example, we see those results for Conoclinium celestinum on the left here and Rudbeckia hirta in the middle here. And again, those analyses were performed for each of the 68 species in this data set. So I used these data to test for changes to overlap for every unique pairwise comparison of species in this data set. So for example, here are those results for Conoclinium celestinum and Rudbeckia hirta, where we can test how flowering overlap has changed between these two species across the past century by overlaying these two results and seeing how their flowering overlap in a historic reference year, which I used as 1940, compares to their overlap in a contemporary reference year, which I used as 2010. The difference in overlap from 2010 to 1940 gives an estimate of how flowering overlap in this pairwise comparison of species has changed across that time. So with 68 species in this data set, there are over 4,000 unique pairwise species comparisons. And we can plot all of those comparisons here shown in this heat map. So what you're seeing here are all 68 species plotted on the Y against all 68 species on the X. Each cell in this heat map gives the results of how flowering overlap has changed for a unique pairwise comparison of species. Red indicates increased co-flowering, that their flowering overlap has increased from 1940 to 2010, and blue is the opposite. They have decreased in flowering overlap across that time. I used the data from this heat map to calculate a net estimate for each species of how their flowering overlap has changed with all other species at the community level by taking, for each species, the sum of pairwise changes to flowering overlap. And you can think about those analyses as, if you think about this heat map as a data frame, and you take the sum across every row, you derive this panel on the right. And the takeaway from this panel is that if you look at this vertical dotted line at 0, which indicates no net change in flowering overlap at the community level, all species to the right of that line have increased in flowering overlap from 1940 to 2010. And thus, we see just a massive increase in heterospecific flowering overlap at the community level at Shaw, whereby all but 4 of our 68 species have increased in flowering overlap across the past century. I also find an interesting seasonal effect of these changes to co-flowering, where if we plot co-flowering richness against day of year, and we do this first for 1940, our historic reference year, we see that co-flowering in 1940 was roughly bimodal. You have one peak in the spring followed by another peak in the summer. If we plot the same data, but for our contemporary reference year, 2010, we see that those two historic peaks have shifted earlier. And we also, interestingly, see the emergence of a novel peak of co-flowering in the fall. My analyses suggest that this novel peak of co-flowering in the fall is essentially the fall equivalent to earlier flowering in the spring, meaning that as temperatures rise and fall ends at a later date now than it did in the past, late season fall species can simply continue flowering until winter finally ends, which has resulted in this novel peak of co-flowering in the fall. That interpretation can be seen derived from these two analyses, where in each plot, each point is a species, and the x-axis of each plot gives the mean day of year that a species flowers. Thus, working from left to right in each plot, you're essentially seeing species ordered based on their consecutive flowering across the growing season. On the left-hand panel, the y-axis gives the number of days that the ending of a species flowering season has shifted from 1940 to 2010, with positive values indicating a delay to the end of flowering. And we see that late season fall species are more likely to have shifted the ending of their flowering back. So they now end flowering at a later date than they did in 1940. And on the right-hand panel, we see, again, a similar plot, but now the y gives the number of days that the ending of their flowering has shifted for every 1 degree Celsius increase in mean spring temperature. And we again find that these late season fall species are more likely to shift the ending of their flowering later in years where temperature is higher. Again, indicating that climate warming has opened climatic niche space in the fall to allow these fall species to simply continue flowering until winter finally occurs and they stop flowering. All right, and now I'd like to circle back to the utility of the herbarium records that I added to this data set. So the utility of those herbarium records lies in the fact that not everyone is lucky enough to have an Edgar Anderson in their past. In other words, it is very rare to have historic data sets of flowering records at the community level. And thus, I was interested in whether herbarium records could be used in the absence of historic field collected flowering data to provide robust estimates of how co-flowering has changed across the past century. And I find that there is remarkable overlap in the estimates derived from herbarium data as estimates derived from field data. So specifically, if we compare the posterior distribution in estimates of the slope of changes to the beginning of flowering and the ending of flowering for every species in our data set, I find remarkable overlap of estimates of the slope, where there's more than 90% overlap of the 80% credible intervals for the slopes. And for the intercepts of those slopes, there's slightly less overlap, but on average across species, it is still 85%, indicating again that herbarium data can be used in the absence of field data to produce estimates of how co-flowering has changed across the past century. So circling back to the question that motivated this work, how do changes to flowering time affect co-flowering richness? I've found that changes to flowering time affect individual species flowering duration, which by increasing species level flowering durations, increase co-flowering richness at the community level. And there's an interesting seasonal effect to those changes in co-flowering, where co-flowering is particularly pronounced in the fall. And herbarium data can provide similar estimates as field data in the absence of long-term field collected data sets. All right, so now on to the second question in the first half of my talk. How does climate change affect angiosperm outcrossing rates? So as I was working through the previous study that I was chatting about of how climate change affects flowering overlap among different species, I began thinking broadly about how herbaria can be used to test outcrossing rates of flowering plants. And through thinking about this question, I landed on one species that I thought was an ideal model for testing this question, which is the common blue violet Viola sororia. And this is an ideal model species for testing how climate change has affected outcrossing rates because the common blue violet has dimorphic cleistogamy. And by having dimorphic cleistogamy, what this means is that individual plants produce two different types of flowers, chasmogamous flowers, which are capable of outcrossing by opening to reveal a showy floral display, which attracts animal pollinators. And these plants also produce cleistogamous flowers, which are obligately selfing and remain tucked near the base of the plant in a reduced bud-like form. There's a trade-off in the production of these two flower types, whereby chasmogamous flowers have the benefit of being capable of outcrossing and thus increasing genetic diversity. However, they are more energetically expensive than cleistogamous flowers. Cleistogamous flowers are cheaper to produce, but they can lower genetic diversity because they are obligately selfing. So in the summer of 2021, I worked with a really fantastic REU student, Piper Cole, to work on a study where we were interested in if herbarium records of the common blue violet could be used to derive estimates of outcrossing rate by taking counting the total number of each flower type on a record and taking the ratio of those two flower types, which we calculated as the proportion of cleistogamous flowers to cleistogamous plus chasmogamous flowers. Hereafter, I'll refer to cleistogamous flowers as selfing flowers, chasmogamous flowers as outcrossing flowers. And we used records spanning 1875 to 2015 to test whether that ratio of the two flower types has changed across that time period. And we also paired our herbarium records to climate data to see if there were climatic associations with the proportion of selfing flowers. And again, the proportion of selfing flowers is an estimate of outcrossing rate, where 0 indicates sole production of outcrossing flowers, 1 indicates sole production of selfing flowers. We focused our study to the state of Missouri, given the strong history of collection in the state here at the Missouri Botanical Garden. So from this work, I find a significant association where the proportion of selfing flowers has decreased from 1875 to 2015, indicating that across that time period, there appears to be greater relative production of chasmogamous outcrossing flowers compared to obligately selfing cleistogamous flowers. There is also a significant association with total annual precipitation, where Viola sororia records are more likely to have a higher ratio of outcrossing chasmogamous flowers to obligately selfing cleistogamous flowers in years where total annual precipitation is higher. Because Missouri has experienced an increase in total annual precipitation from 1875 to 2015, the results of the study are consistent with the hypothesis that as precipitation in Missouri has increased across the past century, we are seeing greater water availability correspond to greater relative production of outcrossing flowers relative to selfing flowers in the common blue violet. So thinking back to the question that motivated this work, I found evidence that in the common blue violet, climate change may increase outcrossing rates, and also that outcrossing rates in species with dimorphic clystogamy may be linked with water availability. All right, and now I'd like to shift gears and move into the second part of my talk, where I'll be chatting about some of my future directions for working with digitized herbarium data. So I have three general directions for working with digitized herbarium data. And the first of these is to apply machine learning to digitized herbarium images. The second is using digitized occurrence data to provide rapid assessments of species conservation status. And then the third is to continue leveraging herbaria, and in particular digitized herbarium data, to explore how environmental variability affects reproduction. So I'd like to start with how I plan to apply machine learning to digitized herbarium records. In recent times, there has been a global push to digitize herbaria, and this is due to increasing recognition of the value to global digitization efforts. Digitization efforts enhance botanical research by increasing global access to herbaria and creating permanent electronic records of herbarium specimens. And as institutions across the globe work to digitize their collections, we're creating a global meta-herbarium, which is accessible by the public. Here at the Garden, we play a significant role in these global digitization efforts through our curation of our over 7.75 million specimens and our curation of tropicals. And my background as an ecologist has shown me the broad uses of digitized herbarium data and the fact that herbaria can truly be used for an infinite number of purposes to answer a variety of questions in biology. Machine learning is an ideal complement to digitization efforts of herbaria. And in recent years, machine learning has been applied to herbarium data in a number of ways. These range from using machine learning algorithms to aid with taxonomic assignment and species discovery, to counting reproductive structures on herbarium images, and the quantification of leaf traits, such as leaf perimeter and leaf area. Machine learning has even been applied to quantifying estimates of plant-animal interactions via herbivory marks, and can assist with label capture through pairing machine learning with optical character recognition. To demonstrate the potential of machine learning for herbaria, I think it's helpful to walk through the general workflow that machine learning takes. So the first step with machine learning is to generate training data, which are human annotated images. And if we take the example of applying machine learning to counting the total number of flowers on herbarium images, training data would consist of human annotated herbarium sheets, where humans have manually indicated the location of flowers on specimens. And this is done by drawing a bounding box around each flower on an image. After training data are generated, they are fed into a machine learning algorithm to train the algorithm on how to recognize that annotation. After the algorithm has been trained, it can be deployed with unannotated images, and the model will predict the annotation of those images. So if we think about the example of using machine learning to count the total number of flowers on herbarium sheets, this deployment would consist of providing the algorithm with specimens of digitized herbarium images that have been unannotated, and the model will predict the location and total number of flowers on each sheet. After deployment, model accuracy can be evaluated by having a human manually annotate a subsection of the images that the model was deployed with, and we can calculate model accuracy based on how closely the model's predictions match the human adaptation. If model accuracy is not at a sufficient level, repeated iterations of training can be undertaken to perpetually increase model accuracy until it's at a sufficient level. And once model accuracy is at a high level, that model can be deployed with truly as many images as you would like. And at this stage of final deployment, machine learning algorithms have a very high processing speed. They can literally process up to tens of thousands of specimens per minute. So there are many types of machine learning algorithms. However, one type that has particular utility to herbarium imagery is one called masked RCNN. And CNN stands for convolutional neural network. Masked RCNN is a state-of-the-art model for object detection and is handy because there is freely available code online that you can just go on GitHub, download the data. It comes with a nice user-friendly guide. And all that you have to do is you can utilize the code for any purpose you want related to object detection. You just have to provide your own training data and calculate your own model accuracy. In 2020, a paper came out that applied masked RCNN to counting reproductive structures on herbarium imagery. And the paper found a very high rate of accuracy for applying masked RCNN to this purpose. Specifically, this paper found greater than 87% accuracy for the binary scoring of whether a reproductive structure is either present or absent on a sheet. And interestingly, they also found more than 90% accuracy for quantifying the relative abundance of reproductive structures, so the relative abundance of buds, flowers, and fruits on herbarium sheets. I'd like to emphasize that machine learning has many, many applications to herbarium imagery beyond just the quantification of reproductive structures. And I would encourage all of you to think about how machine learning might be applied to your work. I would love to form collaborations with folks at the garden, applying machine learning to purposes that would complement their research interests. Essentially, by applying machine learning to digitized herbarium data, especially as digitization efforts ramp up across the globe, machine learning is essentially providing big data to botany. And these large amounts of data can be used, again, for an infinite number of purposes, all of which can ask a variety of questions about how traits vary across space and time within and between species. To fully realize the potential for machine learning applications to herbarium imagery, we need collaboration between biological communities and computer science communities. And I have a collaborator, Nathan Jacobs at Washington University's McKelvey School of Engineering in the Computer Science and Engineering Department, who's decided to collaborate with the garden on efforts to apply machine learning to herbarium imagery. Nathan is an expert in applying learning-based algorithms to extracting trait data from large data sets of images, and he even has an ecological bent. Just this summer, he'll be applying machine learning to automating species ID from camera trap imagery out at Tyson Research Center. There are also a variety of funding sources and resources to support not just digitization efforts, but also how machine learning can complement digitization efforts of herbaria. All right, the second way that I plan to use digitized herbarium data in my future work is by using digitized occurrence data to provide rapid assessments of species conservation status. So I plan to provide rapid assessments of species conservation status by developing a pipeline for using occurrence data to calculate extent of occurrence and area of occupancy, and then by pairing occurrence data with climate data, calculate climatic variability within species extent of occurrence. And climatic variability can help indicate threat level for species in two different ways. The first of which is lower climatic variability within an extent of occurrence corresponds with a higher likelihood of a species being vulnerable to a stochastic event. Second, for species with sufficient temporal coverage in their occurrence data, extent of occurrence can be calculated in a historic time period and a contemporary time period. And by calculating climatic variation in each of those time periods, the magnitude of climatic change between time periods can give us an indication of threat status for that species, whereby a higher magnitude of change may correspond to greater threat level. In this pipeline, I will also use data from the World Database of Protected Areas to quantify the percent of a species' extent of occurrence that falls within a protected area. So by developing this pipeline, I plan for this to be a tool where occurrence data can just be put into this pipeline and these features can automatically be calculated, thus highlighting species with potential for red listing. And this would be, of course, particularly useful for triaging efforts for deciding which species should be considered for official IUCN red list assessment. Finally, I plan to continue using herbaria and digitized herbarium data in particular to continue exploring how environmental variability affects reproduction. And there are many ways that herbaria can be used towards these efforts, but examples of some future projects that I'm particularly interested in pursuing are first, expanding the spatial coverage of my exploration of how phenological changes have affected co-flowering overlap. To date, this work has been concentrated around the greater St. Louis area, but I would love to expand this work to, say, the entirety of the eastern portion of North America, which has experienced similar climatic changes across the past century, notably increases in precipitation. And then I would like to test for how for closely related species that used to have partitioned flowering times and thus a pre-zygotic barrier to reproduction, and which has been shifted to overlap in their flowering time, I'm interested in using herbaria to test whether these species might be hybridizing now, which could be tested by looking at specimens with trait intermediacy or a combination of traits from two parental species. And also looking at maybe these species haven't hybridized, but have begun evolving reproductive character displacement. And finally, I would love to compare estimates of phenological changes with my rapid assessments of conservation status by looking at the relationship between changes to flowering time and changes to extent of occurrence and area of occupancy. And by coupling estimates of phenological changes with estimates of changes to population size, we can provide a rough indication of whether phenological changes are either adaptive or maladaptive. That's currently an open question in phenological literature, and indeed that the answer to that question might depend on taxonomic group. But by using digitized herbarium data to look at the correspondence between phenological changes and changes to extent of occurrence and area of occupancy, we can begin to answer that question in different taxonomic groups and at different scales. So herbaria can be used in many different ways to support botanical research and conservation. And I have used herbaria in the past to look at how climate change has affected plant reproduction. And I plan to continue using herbaria and digitized herbarium data in particular to support botanical research and conservation through machine learning, rapid conservation assessments, and continuing my research on how environmental variability affects reproduction. And with that, I thank you all for coming, and I'm happy to take any questions.